The simplest definition, at least a non-mathematical definition of a derivative, would be the idea of rate of change. How fast is one variable changing with respect to another variable? So I'm just going to look at a very simple example, a straight line with a constant slope. The slope here is 2. Those of you that are familiar with y equals mx plus b recognize the slope here. But I just want to talk a little bit about this first. Slope is rise over run. You take the difference in the y values and you divide by the difference in the x values, and that gives you a measure of how steep that line is or how fast y is changing with respect to x. Now, the idea here is no matter how far apart you pick points on this line, for example, if you pick 1, 3 and 5, 11, and you take the difference, the y difference here is 8 and the x difference is 4, 8 divided by 4 again is 2. And also, no matter how close together you take those points, for example 1, 3 and 1.001, and that's the y value there, once again if you take the slope, rise over run, you come up with the number 2. So straight lines are easy. They have a constant slope and it's easy to recognize. However, when you come to a curve, the rate of change is variable. The rate of change here is very different from the rate of change at other points on the graph. And the other thing that complicates this is you no longer have 2 points to work with, because the rate of change right here at this point is actually the slope of the tangent to that point. So we have to figure out some way of coming up with a slope for that tangent. Now, most courses in calculus start off with a fairly simple non-linear equation like y equals x squared. And if you were to try to figure out the slope of the tangent at, say, p, which is the point 39, you would pick a succession of points that get closer and closer to the point p, because the slopes of those tangents become better and better approximations of the slope. The slope of those secants become better and better approximations of the slope of the tangent at p. So for example, the slope from p to a, 416, is 7, whereas the slope from p to b is only 6.5. P to c works out to 6.1. And now if you take a point even closer, what I did was 3.01, and when you square 3.01 you get this number, 9.0601. The slope there is 6.01, so the argument is made, since the slope of these secants is getting closer and closer to the value 6, we can argue that the slope of the tangent at p is 6. If you come up from below, for example, if you go from 2,4 to 3,9, you get a slope of 5. And once again, if you do the same process from below, you get numbers that, again, get closer and closer to the number 6. So we can argue that we've got the slope of the tangent trapped between these two numbers. Now, this is a lot of work when you're doing it with numbers. So here comes the h. If any of you have seen any of this before, most textbooks use an h at this point. So our point that's close to 3,9, and again we're using y equals x squared. The point that's close to 3,9 is 3 plus h. The h is taking the place of the 0.5, 0.1, 0.01, and so on. So we can do this totally in general for this 0.39. So this is our y value at the x value, 3 plus h. And once again, here's the slope, rise over run, simplified. I factored out the h. Dividing top and bottom by h, we get 6 plus h. And again, we argue that as q gets close to p, the h gets smaller and smaller and smaller, so we're getting a slope that's getting closer and closer to 6. So again, the argument is the slope of the tangent at p is 6. Now, Again, that's a lot of work to do it for one particular point. So let's make it a little more general, and here comes the derivative, which will tell us the slope everywhere. So what we're doing is, instead of 3 and 3 squared, I just have an x squared. I use the h again just the way I did with the 3. It's x plus h and squared. Once again, slope of the secant PQ. Looks like that. Difference in the y's over the difference in the x's. Expand this and simplify. Looks very similar to what we did with the 3. Again, we're going to factor out the h, divide top and bottom by h, and we get 2x plus h. And again, the argument goes, as q gets closer to p, the h gets smaller and smaller and smaller, so we get a general slope here of 2x. Now, if you relate that back, we had a point 39 and we came up with a slope of 6. 2 times 3 is 6. If I take a point where the x is 0, 2 times 0 is 0, that gives me the slope right here, and you can see it is a 0 slope. If I take a negative like -4, I would get a slope of -8 coming down. So this expression right here is what we call the derivative of that function. It tells us the slope everywhere. Now, one final thing before I close here. If we do this totally in general, in other words, I'm not even saying what the function is here. I'm just saying I've got some function of x. Could be x squared, x cubed, could be a sine function, could be anything we want. And here is our nearby point, x plus h, and the function there. Again, it's simply rise over run. All this expression is right here is the rise from P to Q over the run from P to Q. And so our derivative, and this is the symbolism most of us use for derivative, f prime at x, is simply the number we're getting close to, or the expression we're getting close to, as h gets smaller. This is the standard definition for the derivative, and it's a very simple idea. It's just a slope between 2 points as the one point gets closer to the other. Gives us a measure of how fast the one variable is changing with respect to the other. So a derivative basically is simply the rate of change of a function with respect to a particular variable.